Welcome back to Carneades.org. Today we're going to be continuing with the 3 months of Modal Logic, the sequel to 100 Days of Logic. In this video, we are continuing the final 10 days of logic, almost done with this huge series. Today we'll be looking at interval logic and HS notation. It's going to be interval based temporal logic with Halpern, Shoham, and Allen. Now, we have in the past looked at interval logic very briefly. In this video, as you can probably tell by its length, we are going to be doing a much larger perspective on interval logic and really getting into more depth with what the operations and modal laws and axioms are that apply to interval logic. So, at the beginning of our series on temporal logic, we distinguished between instant-based temporal logic and interval-based temporal logic. For the rest of the series, we dealt only with instant-based temporal logic. I did a bit of an introduction to interval logic, but left it at that. That was logic that talked about the relations of specific instants, or moments in time. In this video, we are going to give a basic but hopefully relatively comprehensive introduction to the other kind of temporal logic, which is known as interval-based temporal logic. Interval-based temporal logic does not deal with particular instants in time, but rather with intervals or periods of time and the relation between them. So, Zeno's famous arrow paradox offers one reason that we might want to deal with intervals instead of instants. An arrow cannot have speed at an instant because it's not moving at any given instant, but it must have speed over an interval. If you want more information on the arrow paradox, check out my video on the subject. But it's just a little bit of information of why one might want to use interval logic instead of instant logic. Interval logic is going to be more expressive than instant logic, but it's also going to be much more complicated. In this video, we're going to briefly examine the basic relations of inclusion and overlap and add them to our basic relation of precedence that we had for instant-based logic. Next, we will define point intervals and distinguish between strict and non-strict semantics. We will only be working with strict semantics in this video. Non-strict semantics is a little more complicated, and this video is already going to be long and complicated enough as it is. Then we're going to define the 13 possible Allen relations which can hold between intervals and the Halpern Shoham, or HS, modal operators which act on them. We will then define the HS terms in strict semantics. Not non-strict semantics, only strict semantics. Finally, we will look into some of our modal logic axioms and see if they can be applied to interval-based temporal logic. There's a lot going on here. Hopefully, you can follow along and get a really good sense of what interval-based temporal logic is. So, hopefully you remember if you watched the series on temporal logic, there was a relation we talked about at the beginning called precedence. So, just as instants can be before or after each other, intervals can be before or after each other. In basic first-order logic, not getting into the Allen relations or the modal operators yet, we're going to represent these with the same symbol that we did for instant precedence. The statement P, this kind of curly greater than sign, Q, means that P precedes Q. If you want more information on precedence, check out the previous videos in the series on instant-based temporal logic. So if we wanted to say that the interval of time that you brushed your teeth last night, T, was before the interval of time that you slept last night, we could represent that as T precedes S. As with instant logic, the exact meaning will change depending on the axioms we include. We're not going to focus on these kind of first-order relations that much because we're going to get much more depth and breadth with the Allen relations when we get to them. I just want to do a basic introduction. The next relation here is the inclusion relation. The inclusion relation is a new relation for interval logic. We did not see it in instant-based temporal logic. It means that one interval is completely included in another interval. If we said that x is included in y, that would mean that x is included in y. It's kind of a squared off subclass sign, if you know anything about set theory. So If we wanted to say that the interval that Ricardo called R was during the interval that Papa was visiting, we would express this as R is during, or is part of, is included in the interval P. Once again, these are the basic notations, and exactly how this is defined is going to depend on the axioms included. So depending on how we want to define inclusion and how we want to construe our timeline, we can include several different axioms. So we could include reflexivity. All intervals include themselves. That would mean that if two intervals are identical, then they would include each other. And antisymmetry. If two intervals include each other, then they are identical, as I just said. There are other axioms we can include to better define our inclusion relation, but we're not going to get into them right now. This is just a basic introduction. So the next one is overlap. The third basic relation between between intervals that we'll look at is overlap. Simply, this will hold if two intervals share another interval between them. Exactly how this is defined will depend on the axioms included. If the intervals must each have some part that is not shared by the other interval, etc. Once again, it's going to depend on how exactly we use the axioms to define overlap. Our Allen relations are going to be much more clearly defined. We're going to read OVPQ as P overlaps Q. Therefore, if we wanted to say that the interval of time that Socrates was alive, S overlapped with the interval of time that Plato was alive, P, we would say OVSP. Hopefully, that's clear. As with the other relations, overlap can be defined differently depending on the axioms we include. One possible axiom is the axiom of symmetry. If one interval overlaps the second, then the second interval overlaps the first. It's important to note that this is different than the Allen relation called overlaps or overlapped by. Those two relations are different than this overlap relation. Just because they have the same title does not mean they're the same relation. This one's going to be represented with OV. The Allen relation is going to have a different way of representing it. Hopefully, that's clear. So, there's a great deal more that could be said about these relations, and we could define different timelines based on how we construe the axioms for them, as we did with precedence in instant-based temporal logic. But we're now going to move on to the distinction between strict and non-strict semantics. So, to understand this, we first have to understand what is meant by a point interval. So a point interval is basically an instant. This is one of the reasons that interval logic is kind of more complicated than instant-based logic, because interval logic, at least if you're using non-strict semantics, it includes instant-based logic. So intervals are generally defined by their start and end point. An interval that has the same start and end point is going to be a point interval. The modal constant pi, that you often see representing the decimal 3.14159, and so on and so forth, is going to be used to designate a point interval. Strict semantics that we're going to be dealing with does not allow for point intervals. Non-strict semantics does. And that's going to be the key distinction between strict and non-strict semantics. So we're not going to be seeing much of these point intervals for the rest of the video because we are going to be focusing solely on strict semantics. But if you ever do have to work with non-strict semantics, which also kind of encompasses instant-based logic, you will be seeing this constant as well as other representations of point intervals. Non-strict semantics is arguably more complicated than strict semantics because it includes both kind of the strict interval logic semantics as well as all of the pieces of instant-based logic and the interactions between them. At some point, we may do videos on a non-strict semantics. We might do a series of videos on those. But for the remainder of this video, we're going to focus solely on strict semantics. Now, on to the Allen relations. So, using strict semantics, there are 13 Allen relations from J.F. Allen, which can hold between intervals. These relations are mutually exclusive. No two intervals can have more than one. So each of these intervals cannot bear more than one of these 13 different relations to each other. And they're jointly exhaustive. All sets of two intervals must have at least one. So between those two conditions, all pairs of possible intervals have exactly one Allen relation that holds between them. Only one of these relations, equality, which we will get to at the end, is symmetric. And equality is also the only relation which isn't going to have an HS notation paired with it. All the others are going to be pairs of possible ways that the current interval, or a particular interval that we are talking about, which I'll talk about as the current interval, but you can define differently, can relate to another interval. Now, each of these relations, with the exception of equality, so the first 12 relations we're going to talk about of the 13, has a modal operator over it, created by Halpern and Shoham, hence the HS notation. Each of these modal operators can either be a weak or diamond operator, which corresponds to possibility. So you remember in alethic modal logic, we had diamonds that represented possible, and so we kind of have these letters encased in those diamond brackets to represent kind of a possible or weak modal operator, or an operator that's going to correspond to all those ideas of permissibility, possibility, those kind of things that we saw in other modal logics. And a strong or square modal operator, which will be a letter encased in those kind of square brackets, which is going to correspond to our strong operators in other modal logics known like necessity, obligation, these things. HS notation is interesting in that the weak modal operator is generally more commonly used than the strong modal operator, but we're going to be going into both of them for all of these possible relations. The former says that the relation holds between this interval and some other interval. The latter says that it holds between this and all other intervals. For some statement P to be true, it holds either between some other interval that bears that relation to the current interval, or for all other intervals that bear the relation to the current interval. Looking at some examples, hopefully this will be made clear. So, let's take a look. The first one we're going to look at is this. It is what Allen calls the meets relation, and HS will call the after relation. So we have our first interval, our current interval, the interval we're focusing on, and some other interval. And that some other interval begins at exactly the point that our current interval stops, and then ends somewhere later. This relation holds when the second interval's starting point is the same as the first interval's ending point. We could say that the interval today meets the interval tomorrow, because the ending point of today is the starting point of tomorrow. One could represent this as DMR, or today meets tomorrow. The HS notation, on the other hand, will say that there exists some interval which has the same start point as the end point of the current interval for which some P is true. So there exists some, that's the idea of the possibility or kind of the existential quantifier, there exists some interval which has the same start point as the end point of the current interval for which some P is true. So if we said that AP for some interval V, that means that there exists some interval which starts as V ends where P is true. For example, if you were to say, as soon as today is over, it will be your birthday, you are saying AB for some interval T, where T is today and B is the proposition, it is your birthday. Basically, there exists some period of time that starts right after today is over for which the statement, it is your birthday, is true. Clearly, this statement would be true if tomorrow is your birthday. However, this statement could also be true if our current interval was this week and the next interval was the following day. It'll all depend on how you define the current interval and exactly when your birthday falls in relation to it. Okay? But basically, if we define the current interval as today and tomorrow is your birthday, then A, B, or the interval exactly after the current one, B is true, it is your birthday, will be the case. Hopefully that makes sense. There are plenty more of these relations to look at and understand if you didn't get it there, so let's move on. The other HS notation which relates to this relation is the strong version of the modal operator. As all strong versions of modal operators are, it's going to be defined as the negation of, it's possible that the negation of P. So the negation of the weak operator, the negation of the proposition, is the same as the strong operator on that same proposition. Or in other words, by AP in square brackets, we mean that for all intervals which start the moment that this one ends, P will be true. Or, it's not the case that there exists some interval which starts the moment that this one ends, wherein P is false. For example, after today, our little girl will be an adult, could be codified as AA for the interval of today. Basically, for all intervals which start at the end of today, our little girl will be an adult. Okay? Hopefully that makes sense. This kind of formula of looking at a weak and then a strong operator over an Allen relation is how the rest of these relations are going to go. So if you didn't understand that, we've got plenty more to look at. So next we're going to look at kind of the reverse relation of that one. So the next relation we're looking at is what Allen calls the met by relation, or MI. And HS will call the after relation as well. HS is going to give the same name to every pair of Allen relations, but they're going to do a little bit different symbol. They're going to have that line over the top. That's going to just mean that we've switched the now period and the then period. So as you can see from the diagram, this is talking about relations between the current interval and an interval which directly preceded it, which it was met by. So this relation is simply the reverse of the relation we just looked at. So if V meets W, then W is met by V. Hopefully that makes sense, and hopefully the visual here gives you a good clue as to what we're talking about. This is talking about the relation between a current interval and an interval that directly preceded it, that ended at the exact same moment that this one began. The only difference in the HS notation for this relation is the line on top. As I said, it states that there is some interval whose endpoint is the same as the starting point of this interval, for which some proposition is true. For example, if you were to say, until today, I was in a slump, we could translate this as, there was some interval which ended when today started, taking today as the current interval, where the proposition, I am in a slump, S, was true. Or, for the interval today, A, S. Hopefully that makes sense. Once again, all of these should be following the same pattern. What held true between strong and weak operators for the previous operator is going to hold true here as well. It's going to have that negation on either side of the weak operator once again for the strong operator, and the strong operator is going to be the exact same letter and line on top, but now just with a box around it. So, if you were to say that every period in history before this one moved slowly, you could represent this as, for all intervals ending when the current period in history began, they moved slowly. Or AS. Note that this would not say anything about an interval which started and ended before the current one, other than that it is included in a period of time that moves slowly, since this modal operator only quantifies over intervals ending where the current one starts, rather. Note that these strong operators are going to seem a little weird. I'm going to try to find examples for all of them, but the weak operators actually make much more sense with the examples, which is why the weak operators are more commonly used here. All right, so on to the next relation. So the next relation we will look at is quite similar. It's the Allen relation is known as before and represented with that kind of greater than sign. The HS notation is L in the diamond brackets, and it's called later. This relation will hold when the last instant of the first interval, or the current interval, is before the first instant of the second interval. So Wednesday is before Friday. Note that while Wednesday meets Thursday, it is not before Thursday by this definition, since the moment that Wednesday ends is the same moment that Thursday starts. Wednesday is before Thursday, but it's not the case that Wednesday is before Friday, rather, but it's not the case that Wednesday is before Thursday. Rather, Wednesday meets Thursday. Hopefully that makes sense. So this interval is going to hold when there is some space in between the current interval and the next one, not when they meet each other exactly. The weak HS relation later, or LP, reads that there is some interval whose starting point is after the ending point of this one for which P is true. So if one says, I will go to the bank tomorrow, if we take the current interval as today, then we can translate this as there exists some interval, the time period when I'm going to the bank, when it is the case that I am going to the bank, which has an interval in between it and the current interval. It is later than the current interval. And this will hold so long as I don't leave for the bank exactly at midnight, exactly when today started. That would be the after relation holding, the A in the diamond brackets. But as long as there's an interval in between the current interval, today, and the time period in which this is true, this interval is true, then we can use the later modal operator. Similarly, the strong relation is going to be defined as for all intervals after this one, which are not directly after this one, P is true. As with the after relations, it can be defined as all strong and weak operators are defined. If we take the current interval as today, for example, and one were to say, I will never be as happy as I am today, we could translate this as there is no interval which starts after this one in which I will be as happy as I am today, or L, not H. Though it's important to note that this would not discredit you being happy for the first two instants of tomorrow, but it would discredit you for being happy for any instant following that. This may seem similar to AP, but remember that the intervals covered by AP must start right after the current interval, while the intervals covered by LP cannot. To count out the first two instants, you could state both L not H and A not H. Once again, note that these strong relations are not going to make as much sense. They're not going to fit into normal language as well as the weak relations are going to. But I'm giving you examples just to hopefully give you a better sense of what exactly we mean by these wide variety of different modal operators over intervals. Now, just as we had the reverse of after, we are going to have the reverse of that relation. This is actually going to be called after by Allen relations, not to be confused with the after that we looked at previously in HS notation. This is the problem with having 13 different relations and having to come up with different names for all of them, and L or later in HS notation, but now we have an L with a line over the top of it. Just as before, this interval will work in reverse from the before Allen relation. Friday is after Wednesday, F with that greater than sign W, but it's only met by Thursday. Friday is met by Thursday, but is after Wednesday, for the same reasons that we discussed of Friday is after Wednesday, but it is Wednesday meets Thursday. Hopefully that makes sense. Apologies if it's getting too confusing. There's a lot of different terminology here. So, similarly, the weak reverse of later, this kind of diamond L, will make claims about some interval whose final moment came before the first moment of the current interval. Therefore, if we said Shakespeare lived before the 21st century, and we take the 21st century as the current interval, we could translate this as there exists some interval which ended before the current one where Shakespeare was alive. Once again, these diamond intervals make a little bit more sense than the square ones, which is why they're more commonly used. The strong reverse of later will follow the same pattern. LP can be read as for all intervals which ended before this one started, some P was true. Once again, it's going to be defined with that kind of two negations on either side of our possibility or diamond operator. If someone said, today is the best day of my life, we could translate this as for all intervals that ended before this one started, it was not the case that that day was as good as today. Note once again that we cannot exclude the interval that starts an instant before today does and ends the instant today starts, without also stating for all instants that are stop directly as this one starts. It's not the case that it was a good day. All right. Once again, square intervals are a little more tricky. Square modal operators are a little more tricky. Hopefully, this is all making sense. So, next up, the next relation we're going to look at is called by both Allen and HS overlaps, represented by O, O, and O, respectively. Hopefully, this won't get too confusing because there are 3 different systems that call different things overlaps. We had the overlaps of the just basic relation from earlier, which wasn't very clearly defined and would be defined differently depending on the axioms you use. We have overlaps, which is the Allen relation, which only refers to this specific relation, and the HS notation, the HS overlaps, which is a modal operator that operates both on this arrangement as well as the overlapped by Allen relation we're going to look at soon. It's a little bit complicated, but hopefully the pictures help. So, the Allen relation will hold when the first instant of the second interval falls in between the first and last instant of the first interval, and the last instant of the first interval comes before the last instant of the second. If you, once again, look at the picture to make sense of it, they overlap each other. For example, the life of David Bowie overlaps the life of Justin Bieber. Once again, hopefully this makes sense. So, the weak HS modal operator states that there exists some interval where P is true, which is overlapped by the current one. So if we said, before today is over, you will have a new kidney to keep for the rest of your life, where today is the current interval, we could state this as there is some interval that starts in the middle of today and ends after today, assuming you live through today, where it is true that you have a new kidney. That period where you have a new kidney overlaps the current interval today. Hopefully that makes sense. The strong HS modal operator states that P is true for all intervals which are overlapped by the current one. It can be defined, once again, as with all of the strong modal operators, as putting the negations on either side of the weak operator. Imagine that the current interval is March 2016. We could say that for all intervals that are overlapped by this one, Alan Rickman is dead. Because Alan Rickman died before this interval, no interval which is overlapped by this one will it be true that Alan Rickman is alive. Hopefully that makes sense. And hopefully we don't have to kill any more celebrities to make the rest of these make sense. So, next up, we're going to switch them around as before and look at the reverse of this relation. So the reverse of this relation is going to be overlapped by, or OI for Allen relations, and O or O with the lines of the top for HS notation. So as before, overlapped by will work in the opposite way that overlap did. If X overlaps Y, then and only then is it the case that Y is overlapped by X. X overlaps Y if and only if Y is overlapped by X. So the life of John Roberts is overlapped by the life of Antoine Scalia. Oops, I guess we killed another one. So the reverse of the weak modal operator of overlap, O with the line over the top, P, will claim that there exists some interval which overlaps the current one where P is true. Some interval which started before this one and ends in the middle of this one for which P is true. If we were to take the current time interval as this century and claim that Saddam Hussein's life overlapped with this century, we could translate this as there exists some interval which started before this century and ended during this century for which Saddam Hussein was alive. Hopefully that makes sense. I will keep saying that at the end of every image because this is a really, really complicated concept in logic, and temporal logic was already a pretty complicated logic, so this is pretty tough. If you are following along, I'm very impressed. Give yourself a pat on the back. So, the reverse of the strong modal operator will be represented with O with a line over it, P in those square brackets, and can be read as for all intervals which overlap the current one, P is true. It is defined as with all of the strong operators, as with the double negations on either side of that possibility bracket. Take the current interval as this minute. For all intervals that overlap this minute, so start before and end during this minute, the universe has existed. Note that the universe doesn't need to stop existing this minute for this to be true. All we are saying is that for all the intervals that start before this minute and end during it, the universe exists. Depending on if you think that time extends back before the universe existing, this may or may not be a true proposition, but hopefully at least it illustrates the point. Now, because all of the rest of the relations are going to follow the exact same pattern that we have looked at, we're going to speed things up a little bit. The remainder of the relations and modal operators will follow this basic pattern. So we're going to speed it up a little bit. The next Allen relation is finished by, Fi. Some interval is finished by another interval if both intervals have the same final instant, but the second interval has a later first instant than the first interval. The HS notation for this is ends, with diamond brackets around the E for weak and square brackets around the E for strong, which means there exists some interval where P is true that finishes the current interval. And for all intervals that finish the current interval, P is true, respectively. Therefore, this work week is finished by Friday, could be represented as W is finished by F. This close basketball game will be finished by a period of time where many fouls are committed, could be represented as EF, and for all periods of time that end the month of December, James will be 46. Hopefully, all of those make sense. Once again, this is following the exact same pattern that all of the previous intervals did. All right? We're just speeding it up a little bit. Once again, look at the picture if it doesn't make sense. So, the next one we're going to look at is the reverse of the previous one, which is going to work, as always, in the exact opposite way. If X is finished by Y, then Y finishes X, and vice versa. So, EP means that there is some time interval where P is true, which starts before the current interval and ends at the same time as the current interval. And EP with the square brackets means that for all intervals which end at the same time as the current one does and start before the current one, P is true. As before, the strong is going to be defined with the two negation signs on either side of the week. The hour from 11 p.m. to 12 p.m. finishes the day. Our lives up through today have been unbearable. And the uniformity of nature has held up through this minute. All right? So note that all our lives mean that there exists some period of time, note when we were born and up through today, where things are unbearable. Whereas the uniformity of nature has held up through this minute is talking about for all, going back all the way through time as far back as you can go, for all intervals that end at the same time this minute ends, the uniformity of nature is true. Hopefully that makes sense. Now, moving on, we're going to look at next the relation that Allen calls contains, or DI, and HS is going to call during, D and D. One period of time contains another if both of the endpoints of the second period are between the endpoints of the first. The meaning of the diamond bracket dP is there exists some interval during this current interval for which P is true, while the square bracket dP means that for all intervals contained in this interval, P is true. As always, the strong interval or the strong modal operator is defined as having the negation on either side of the weak modal operator. Therefore, Bastille Day is contained in July. During Booba's life, he will go through puberty, and every minute of this meeting has been overwhelming. Note that for that last one, we're not counting the first or the last instance. pair of instants, the smallest possible interval you can get at the beginning and the end, because for those we would need to say finishes and starts. Okay? We're counting every minute during the meeting, every minute that's contained within the interval. Right? Hopefully that makes sense. Now, the next relation we're going to look at is called the during relation by Allen relations, or DD by HS notation. As always, it's going to be a reverse of the previous relation. One interval of time is during another period of time if its first and last instants are after the first instant of the second interval and before the last instant of the second interval. dp in the diamond brackets means there exists some interval which contains the current interval for which p is true. And dp in the square brackets means that for all intervals which contain this one, p is true. And once again, we will define it with the two negations on either side of the diamond brackets around the d for the square brackets around the d. Therefore, Thanksgiving is during November, can be written as thus. Today is the third day of the week-long workshop. We're not perfectly going to translate that. Basically, we're saying that our current interval today is during the period of time of the week-long workshop. It's not the first interval. It's not the last interval. It's somewhere in the middle. It's not saying that it's the third day necessarily, but it's saying it's somewhere in the middle. And every period of time that contains this year contains part of the 21st century. Hearing C. Once again, that should make some degree of sense. As with all of these, they are all following the same pattern. So if you can understand any one of these relations, it should very much help you with all of the others. Okay, the next relation that we will look at is known as started by, or SI for Allen relations, and begins B and B for HS notation. One interval bears this relation to another if and only if they are started by the same instant, but the last instant of the second interval comes before the last instant of the first. So this is kind of just the opposite of finishes or finished by, if you think about it like that. BP can be read as there exists some interval which starts at the same time as this interval, but ends sooner, for which P is true. And in the square brackets, BP can be read as for all intervals which start at the same time as this one, but end earlier, P is true. Therefore, 2015 is started by New Year's Day. Moving to a new house requires a period of adjustment, which starts as soon as you move in, but doesn't extend the whole time where you're living there. And you can meditate as long as you want today, so long as you start at midnight and end before the day is over. So M can be true for any period today, so long as, or it's true for all periods today. Our can and is are getting a little mixed up there, but hopefully you get the basic idea. The period of time which M is true has to start at the same instant that today starts and end before today ends. Now, finally, the 12th Allen relation, and the last one that's going to have modal operators on it, we will look at is starts, or S. And the last to have a corresponding pair of HS modal operators, B and B in diamond brackets and square brackets with the lines over the top. As before, the line on top will designate these as the reverse of the original begins modal operators. Some interval starts another if and only if the second interval is started by the first. Once again, just the switch around, look at the picture to better understand it. BP means there exists some interval which is started by the current one, for which P is true. So the hour from midnight to 1 a.m. starts the day. You will feel jet lag for more than just the first hour. There exists some period of time longer than the current period, this hour, for which you will feel jet lagged. And starting today, everything will be different. For every period of time that today starts, things are going to be different. All right. That was the tough stuff. If you've understood all of that and made it all the way through all of those brand new modal operators, that's fantastic. When you think about it, you've just learned as many modal operators about as we learned in the entirety of our modal logic series. So congratulations, great work. Now, there is, however, one more, lucky number 13 Allen relation, which is equality. The final Allen relation does not have a corresponding HS modal operator. This is the equals relation, and it applies when two intervals are equal. They have the same starting point and ending point. If we wanted to say the amount of time that Mr. Dessen and the amount of time that Miss Knowles slept was the same, we could say that D equals K. Pretty simple, that last one at least. Now, we can define all 12 of the weak modal operators in terms of 6 of them. And all of the strong modal operators, as we've shown, can be defined in terms of the weak modal operators. Now, our L is going to be materially equivalent to 2 of our A's over a P. And it's just going to be the same for all of them with the line over the top. During is going to be materially equivalent to begins and ends for P, and once again, the same with the lines over the top. And overlaps is going to get even more confusing. It's going to be ends and then begins for P, and those are going to switch for the line over the top, O. Now, all of these look pretty confusing, so we're going to go through them one by one to really understand what each of these is saying. So, there exists some interval of time such that P is true that is later than the current one. There exists some interval later than the current one for which P is true is materially equivalent to there exists some interval after the current one such that there exists another interval after that interval for which P is true. So basically we have some interval that's after, and then we have some interval that's after that second interval, which is later, which is really just how we defined this earlier. And for that final interval, P is true. This is how we defined it earlier. So our later modal operator is just going to define some interval that has another interval's worth of space between now, the current interval, and that interval. Seems pretty intuitive. This is going to go the opposite way. So there exists some interval that the current one is later than, for which P is true, is materially equivalent to there exists some interval that the current one is after, which itself is after some other interval for which P is true. So we have now, we have another interval that meets now, and another interval that is before now. And that interval that's before now, or that L with a line on top of it, P, that is going to be where P is true. Once again, as with our afters, this is just how we kind of understood that relation of being before. Not meeting or met by, but being all the way before, having some interval in between the current one and that interval. Hopefully that makes sense. Now, there exists some interval during the current interval for which P is true is materially equivalent to there exists some interval which begins the current interval, and there exists some interval which ends that interval for which P is true. So we have our current interval now. There exists some interval which begins that current interval, and there exists some other interval which ends not the current interval, but the interval we were just talking about that begins now, for which P is true. Since our begins line can't extend all the way to the current interval, it can't cover all of now, because then it would be equals, it has to end before now does. And since our ends interval has to not cover, once again, the whole begins interval, it has to start after the begins does, we end up with a during interval. Okay? And for that interval, P is true. And this is just going to be the opposite. The current interval is during some interval for which P is true is materially equivalent to there exists some interval which is ended by some interval that is begun by the current interval for which P is true. So we have our current interval. We have an interval that is begun by the current interval, and an interval that is ended by the interval that's begun by the current interval. And for that last interval that's ended by, it is the case that P is true. Hopefully, you can understand a little bit of that. If you are having trouble with these, go back to the original definitions of all of these different modal operators that we looked at, look at them again, and see if you can make a little bit more sense of them. But hopefully, it can be clear how we are combining these different modal operators to get new modal concepts. Next up, overlaps. So, the current interval overlaps some interval for which P is true is materially equivalent to there exists some interval which is begun by another interval which ends the current interval for which P is true. What does that mean? So we have now, there's some interval that ends now, and there's some interval which is begun by that interval. And for that last interval, P is true. So our last interval is begun by an interval that ends the current interval. Once again, hopefully that makes sense, and hopefully it's clear that that last interval does in fact overlap now, and will forcibly have to overlap now. And we're just going to reverse this for our opposite overlap, our recursive overlap. There exists some interval which overlaps the current interval for which P is true is materially equivalent to. There exists some interval for which P is true, which is ended by an interval that begins the current interval. So that interval for which P is true is ended by some interval which begins the current interval, which begins now. Hopefully, you have a good sense now of the way that we can define all of these operators in terms of just those six. Now that we have clear definitions of all of our modal operators, let's see which axioms we should include in our interval-based temporal logic. If you want a challenge and you've been following along with the whole series, give it a try yourself, because you're probably well aware of all the axioms that we have in the different modal logics. If not, watch the video at the beginning of the final 10 days of logic where we go through them in summary. And try yourself to figure out which of these axioms are going to apply to each of these operators. All right. If you've already done that, or you just want to continue, let's get started. So, axiom K, we remember, goes like this. If P implies Q for all intervals that immediately follow this one, then it seems that if P is the case for all intervals immediately following this one, then Q is also going to be the case for all intervals immediately following this one. It seems that all of our strong modal operators are going to include this, and it doesn't seem that anything is going to not include this, which really defines them very well as modal operators because they conform to axiom K, really the beginning point of modal logic. What about axiom D? So if P is true for all intervals that overlap this one, then P is true for some interval that overlaps this one. With different modal operators, this axiom can imply no end to our timeline, no beginning, or that our timeline is dense. For more information on why this might be, check out the videos on no end, no beginning, well-ordered temporal logic, and so on. So, these are all going to imply no end, these are all going to imply no beginning, and these are all going to imply that the timeline is dense. Note that some of them fit in multiple categories. Okay? Hopefully, you have a good sense of this. If not, like I said, you should really check out the videos on instant-based temporal logic to see what causes something to imply that there is no end, no beginning, or that the timeline is dense. Next up, axiom T. If P is true for all intervals which contain this one, then P is true for this interval as well. This seems to hold so long as our statements are not about maybe the size of the intervals themselves. So these three are ones that are included, while the rest probably don't include axiom T. Basically, all of those where the larger interval is in some way bigger than the current interval probably are going to like axiom T, while the other ones may disagree with it. Hopefully you understand why that's the case. If not, check out what those specific intervals are and what they do to see if you agree. And if you disagree and think that axiom T does not hold for those, or holds for one of those that I say that it does not, write in the comments below and we'll check it out. Next up, axiom 4. If sum p is true for all intervals which begin at the current interval, then for all intervals which begin all intervals that begin the current interval, p is true. This makes sense since the second seems to be a subset of the first. It seems, in fact, that all of our different modal operators are going to fall under axiom 4. But there may be some implications of including axiom 4 in our system. If you think you've found one of those implications or you disagree with this, as before, write in the comments below. Next up, axiom 5. If there exists some interval which ends the current interval, then for all interval for which p is true, then for all intervals which end the current interval, there exists some interval which ends the current interval for which p is true. This seems to me to be false for all modal operators. But, as before, if you think you can work one out for it, explain why in the comments below. Alright? Those are our main axioms. If you want to give it a try with some of the 0.2, 0.3, 0.4s, go for it, or the W's and the Q's, please be my guest. Interval-based logic is more expressive than instant-based logic, but it is also more complicated. We had only 2 strong modal operators in instant-based temporal logic, and it was pretty complex. In interval-based logic, we have 6, and 6 more that can be defined in terms of those first 6. Hopefully, though, this has been a helpful introduction to interval-based modal logic. Up next, we are going to be looking at the final video in this part of the last 10 days. This was kind of an advanced temporal logic before we did a bit of an advanced deontic logic. Up next, we're going to be doing an advanced doxastic logic, which is actually very different than doxastic logic, looking at the logic of belief revision, an introduction to the AGM model. Watch this video and more here at Carneades.org, and stay skeptical, everybody.